So great, that's a Markov chain that describes the states that we can go through, and we can sample state trajectories by just, rolling the dice through probabilities. But, that doesn't really tell us whether it's good to be going through a state or not. And for that, we have to attach rewards, right? So we talked about in the last pre-lecture class, the idea of getting rewards and then trying to maximize rewards is the name of the game here, right? So we're going to start by formalizing what a Markov chain is when we attach the idea of rewards to it. Okay, and this is going to be called an MRP, a Markov reward process. And it's similar to the Markov state, Markov chain, right? A Markov chain, we only had two pieces of information. Now we're adding another two. We're adding a reward variable and a discount variable. Okay, so the two ones in black we already know about from before. So let's just concentrate on the two new ones. So script R here is a reward function. It's a function that's conditioned on a state. So we're going to say everything is encoded into a state. That's because we have this big, nice M word here, a Markov process, which basically says that whatever rewards we want to attach to are going to be modeled in a state. Okay, so knowing what state we're in is going to tell us exactly how much reward we're going to get. If we have differential rewards per state, then basically we need to take that state and separate it into two and say that each of these different states actually have different rewards, okay? So that's an easy way to deal with it. So we can just simplify the process down to having a single state that has a fixed reward, okay? And we're going to say that reward is going to be the expectation of the rewards that you would incur at the next time step. Okay, if let's be clear about this. You enter a state, okay, and then after exiting the state, as soon as you exit the state, you receive the reward for that state. So reward at time t+1 is the reward for being in the state at time t. Okay, so this means when I'm at a certain state at the time step t, then the expectation is once I go away from this time step, I receive a reward value, and I'm going to take that as the reward function, okay? And we're also going to need something else. So the reward function specifies this nice thing where we can say reward is connected to a state, but we might also want to think about a discount factor. Okay, we'll talk about this shortly. The discount factor is going to be some floating point number between 1 and 0, helping us to decide how much we value current rewards over future rewards. So let's take a look at a student, the same case with rewards incorporated. Okay, so we can say, for example, starting at class 1, as soon as I leave class 1 state, okay, either by going to Instagram or by going to class session 2, I've spent some mental capacity and I've incurred a negative reward. So it's like a time step. I've incurred some cost for that. So I'm going to say I have a -2 reward for that. Okay, if I go to Instagram, for example, and I spend time looking at that, that's also consuming time. So I'm going to lose some credit of time here. So I'm giving myself negative reward for every time I visit Instagram or browse Instagram. And you can see here for all of the class sessions, I've just initialized, not initialized, set the reward to a negative number. But let's say I complete all the classes, I take the final exam and pass, and have a nice positive reward. And then when I get to the terminal state, let's just say we don't get any reward for that, we go to sleep, okay? But there's also the possibility that I go clubbing. Maybe I enjoy clubbing and I recoup some energy from that, so I give it a +1 as well, okay? So now, in addition to the probability transitions that I have here, I have now attached rewards. Remember, rewards are the case where we take the reward after leaving the state. So once we've entered the state, we don't get the reward for that. So the reward for getting into the state is actually associated with this one here, right? This -2, that is incurred after leaving class session 1 by either direction, okay? So now what we can do is think about the idea of returns, right? The return that we are getting, we can say it's a random variable G is going to be signifying something like a goal, right? This is what we're trying to do, okay? Maximize our returns, that's what we want. And we're gonna give it a time stamp, okay, for a particular time, okay? And we can say this is going to be the total reward that I'm able to get from this particular time step all the way to the end of the episodes, okay? So depending on how I take a trajectory through my Markov chain or a Markov decision or reward process in this case, I'm going to sum all of it together and encapsulate it in GT, okay? And we can write this out. This is really easy to say. You can say what we're doing with the goal is saying, well, I'm going to get a reward for being in this state, right? I told you that after we exit the state, we get a reward from the next time step, but that reward is for the current state. But we also get all of the rewards going all the way until the last time step, all of these ones here, okay? But maybe we discount it a little bit, okay? So what we're saying is the future time steps, all of the ones over here, are going to be discounted, right? We're going to discount it by some probability. And what we're just going to say is that the discount is multiplicative, right? So after every successive time step, we're going to multiply this discount by itself once more, and then multiply this discount against the actual reward, right? So for the first time step after the current time step, I'm going to discount the reward by gamma and then multiply it by the reward I would be getting at that state. That's this number here, okay? And then so on and so forth, okay? So we can get an idea of what's going on here, right? So if we set if we set gamma equals to 0, right, then basically all of these terms over here will cancel out. They'll all go away, and I'm left with just the immediate time as the reward, right? So this is a very nearsighted evaluation, basically to say, I don't care what's going to happen in the future. I just want to find, given where I am right now, where should I go, right? So that's my immediate award for being in this time step, in this state, okay? And if I set it equal to 1, well, I get a far-sighted evaluation here because basically all of our gammas have gone away, and I'm basically summing up all of the rewards, all of the ones from here, all the way to here, without end, okay? So I can add them all together and then say, okay, that's going to give the sum total of my goal for being in this time step, okay? Now, of course, you can imagine there's some problems with this type of far-sighted evaluation. For example, I might have a very long set of states for a sample, and that means I'm going to favor longer samples over any other thing because, of course, all things being equal, longer samples should have more reward because each individual sample will have a positive reward, for example. Okay? So, you know, we incorporated this idea of a reward, which makes a lot of sense in trying to model what things we should do, right? A particular action should have a reward, but it's not that obvious why we should have a discount, right? So a lot of our processes that we're considering have a discount factor, and the question is why? So think about it for a second. If you'd like, pause the video and then continue. Okay, now that you've considered it, let's think about why it is, okay? Now, there are lots of reasons why, so let's just go over them in turn, all right? So first of all, it's actually quite mathematically convenient for us to have the discounted rewards because the math works out very easily, especially if we take the case where the discount is multiplicative in each time step. okay? And it also helps us avoid that problem of infinite cycles in cyclical Markovian processes. Just like the one that we saw for the student processes, some states can recurse back on itself. And if there's a potentially positive signal over a cycle, it can just endlessly sample that positive cycle to get an infinite amount of reward, which may not be exactly what we want. Okay? I guess the most important one that we'd like to say about discounting is that, there's a lot of uncertainty about what happens in the future. So in many cases, in agents that are traversing the space, either in the real world or in the virtual environment, things change, right? So a stationary process may not describe everything as nicely as in the real world, and that dynamicity might not be accounted for. So we would prefer to take immediate rewards over future rewards just because we're not quite sure what's going to happen in the future. And that variance isn't quite captured in the formalism that we're introducing to you today. It also has an intuitive bent in the sense of financial reasoning. So we'd always think, money in hand right now could be used to invest in the future. Therefore, the future's the same amount of money in the future is worth less than now, right? So immediate rewards could earn some interest, and that qualifies it to be more valuable than money in the future, or delayed rewards in the future. Okay, and from a psychological perspective or a sociological perspective, even animal and human behavior has shown in field studies to show preference for immediate reward. We all have heard of the donut reward system for children to see whether they have the possibility of having delayed gratification, which might help them later on in life. Okay. Okay, all of these things said, we can still actually use the case where we use undiscounted rewards, right? That means we set our gamma equal to 1. So we just say, just sum up all of the rewards together, and for a particular sequence, that is the amount that you get. And we can do that when we are sure that all sequences terminate, when you always make sure that you can reach a terminal state. Then it's still possible to do that. Even in the case where we would do this, we might look at average rewards rather than total cumulative rewards. Okay. All right, so now that we've defined reward and gains, we can define the value functions. So a value function we're going to start with is the state value function. And the state value function gives the long-term value of being in a certain state S, okay? So since we have a Markovian property, everything we need to encode is within the state. So we're going to say that the value of being in the state is equal to the case where we're given that we're starting in the state. What is the expected gain from being at that time step to all of the future time steps, right? Because our gain is defined as the cumulative rewards possibly discounted from being in a certain state, okay? So we're going to have to take the expectation over this because there are many different possible GTs we might have. For example, if we start at some state S, we might go one particular trajectory and get one GT, but we might have gone through another one that has a shorter sample chain length and get another GT, etc., etc. Okay, so we're going to have to sum and average all of these things together, okay, and divide through all of the different trajectories we might sample or samples, and then that's going to define our value function for this state. So to make this concrete, let's take a look again at this student MDP here. Sorry, not an MDP yet, but an MRP. Okay, so now we have, in addition to the Markov chain, we have the rewards that are sitting at each time step, at each state, and we incur or receive the reward once we exit the state. So we're going to say starting from the first state that we have, okay, which might be here class session 1, okay, C1, okay, and with a discount factor here, you can see all over here, these are powers of 1/2, so we'll just say 1/2 here. What we're going to do is calculate the goal that we have for a particular trajectory or a sample, right? So that is going to be the rewards incurred from leaving that state, plus all of the future rewards that we would see here. For example, the reward for getting into the next state would be incurred at time step 3, which would be reward free, but it would be discounted by whatever we set our discount factor to, right? We're going to go all the way to the end of the reward sequence and add all of these together, and that is going to be our total expected gains, or our goal for being coming from state S1 at time 1, okay? So again, using the same sample trajectories as we saw last time, 1 here, 2, 3, and 4, we can calculate what the amount of goal that or gains we would get from going from that state all the way to the end, okay? So at time 1, if we go through C1, C2, C3, past the sleep, I will incur all of these rewards here. Okay, so you can see there's no reward for being in at the sleep state, so we can just neglect that off of the end here. Okay, and we total all of these things together. We're going to get the -2 at the beginning for being in state class session 1 and leaving that, but then the subsequent rewards are going to be discounted, right? Discounted 1/2, discounted to 1/4, discounted to 1/8, going all the way through. When we total all of these things up, we'll get -2.25. Okay, now, you know, that's not the only sample that we have. We have a couple other ones here. But basically, we want to go through all of the possible samples, right? There might be many more. And we're going to sum total all of them and divide through. And we're going to get an average amount. That's going to be the expected value of being in this particular state, given all of the time steps and possible samples that we can get through. Okay, so here's what it's going to be like for the case where we have a gamma equals 0. So try to think about what all of these question marks are. So when we set the discount to equal 0, that means all future rewards are not important. Okay, we're just looking for immediate reward. And hopefully you can get an idea of what that's going to be, right? So that's going to be exactly equal to the reward of leaving that particular state, right? Because I'm going to incur it right after I leave. So if I was in state C1 and I'm trying to calculate the state value function where there are no subsequent rewards, just the immediate reward, that would be the reward of leaving this state. So it would be exactly equal to whatever the reward is, right? So here we have 0, 0. If I'm in the state passing 10, then I would get an immediate reward 10 when I leave that state, okay? So very simple. But, you know, it doesn't have to be so simple. In fact, that doesn't really realistically describe what we think of when we do planning, because we take the future into account. So what happens if we change it to something like 0.9, which means that we, you know, give the weights of future rewards a 10% discount on average per time step we go for. So then we would get different results, and you can see it coincides with what we might think about. This plus 10 here is starting to offset rewards going backwards. So you can see a positive value for all of these states here, mostly due to this plus 10, a little bit due to this plus 1 over here. But this cascading coming back is going through here, right? So you can get the idea of what's going on here. It's going down a little bit here because, of course, going from this time step, we have a 0.6 probability of going forward to get to plus 10, but I also have a 0.4 probability of going to the club, and that's going to take me down a notch at least, because once I go back through here or here, I will have incurred some negative cost getting to the same step. Okay, How about if we don't discount any rewards at all, we just sum up all of them ad infinitum until the sample is done when I hit the terminal step. Well, then we'll get something like this. You can contrast the ones from the previous slides and see that these are slightly more positive in value. Not surprising again, because we're discounting less as we go back. But of course, you can see that on this side, it's gotten a lot worse. Why is that? Because you can see here, once we go through this case here, we are getting a lot of cases where we're going to just recurse through this, because the value of this transition is 0.9, right? So it's a very high likelihood we're going to get stuck in that state, transition a whole bunch of times before reaching back out, and that's going to affect the value of the state a lot. So contrast this slide versus the previous one. This was just a -5, and this was -7.6, but they've gotten a lot worse in this case due to that particular large state transition there. Okay, so we would like to be able to calculate this without eyeballing it. And so what we're going to do is write this down as an equation, and this equation has this recursive idea embedded into it. And we're going to do this for these Markov reward processes, okay? So we're going to say that the reward function, that the value function can be really decomposed into two basic parts. We've got the immediate reward for being in that particular state that we incur or receive when we move out of that state, plus the discounted value of the successor state being in a new state as t+1, whatever value that has, discounted by our discount factor. So we can see here that we have expected value. Okay, this is how we defined it before, and we can just unroll this a little bit. So roll it all out. So that's going to be just what our definition of GT is. GT is equal to the reward of being in that particular state, plus the discounted rewards at all of the other particular state, given that we're in this starting state to be with. Okay, and now we can collect this. We can take the 1 gamma factor out of all of the rest of them here. Okay, so we're just taking this 2 down, and reflecting it would have a 3, a 4, and a 5, and 6, etc. Taking that 1 factor out, and then taking parentheses around the rest. Okay, and then we'll see, hey, this particular thing that I've underlined in red is actually the goal, the gains that I would get at t+1, right? So I can just rewrite it at that. And using this, we can, again, arrive at the idea that this is just the value function over the case for the next state, right? So the state going forward, okay? So just to make clear about this, the reason why we write t+1 here is because by convention, we're indexing time steps. In the case where an agent is making an action at time t, and then our environment is receiving that action at the same time step, but as soon as the time step is, the action is received by the environment is changing with respect to that action, and we're advancing the time step by 1. So here you can say it emits some observation, changing the state in t+1, and emits some scalar reward, which we're going to receive at the next time we exit this new state. So now we'd like to be able to take this and formalize it into some type of recursive equation, and that's going to be our Bellman equation for MRPs, or Markov reward processes again, right? So we have this state value function, which is dependent on the state. And we're going to say it's going to be equal to the expectation, right, of all of the traces that we can get, all the samples we can get, where we start from a state at time t of being in a particular state S, okay? So that's going to be the immediate reward that we have at this state, right? This is the one here, okay? Plus any discounted future rewards that we're going to incorporate through our value function, but not at the current state, but at the next state at time t+1, which is going to be, let's say, for example, our S prime here, okay? So we can write this down like this, right? I'm going to say our state value function is going to be the rewards, okay, plus the discounted value of being in a new state times how likely it is to get to this new state that's given by my transition matrix, my probability state transition matrix here, for all of the states where I can reach from state S, okay? And so let's verify that that actually works out, okay? So let's pretend all the values in this diagram are correct, and we would like to evaluate whether in fact they are correct or not. And I can do that, okay? So let's take a look at this case of 4.3 here. How did I get this value? How do I validate this is correct? Well, I'm going to have to do it recursively, because to get this value, I have to first incur this -2 over here, but then I'm going to have to add my future rewards, right? So let's say in the case where I'm looking ahead only one time step, I can say it's going to be with a 0.6 probability that I'm going this way, and then I'm going to trust that this +10 was actually done correctly. Okay, if it's correct, then I'm just going to plug it in here, and that this +8 is done, 0.8 is done correctly. I'm going to plug it in here, and I'm just going to sum all of these together. The reason I sum these together is basically because it's an average, because we've already normalized our state transitions to 1. Then I will get a total of 4.3 here. You can verify that the math is correct. Okay, so this is the case where we can validate or verify that this 4.3 is correct, given some information that its components are already quite correct. Okay, they need to be correct for me to calculate that. Okay, so we might be able to recursively step back to get these calculations correct. Okay, and the nice form about this is because we're using expectations, it happens to have a very nice linear form, and this linear form has a nice matrix form as well. Okay, so we can express it directly by saying something like this. I have a vector v, which is going over all particular states, so it's a column vector, and it's going to be equal to the rewards, which are also a column vector for being in that particular state. Plus a component which is another particular, which is going to be another particular case where we have a discounted value times a probability transition matrix times a column vector, which is going to yield us another column vector. Okay, so we can do all of this in this type of notation over here. Okay, quite nicely. So we'll get basically two scalar values, an R1 and something this times this, which will give us another you know, P of 1 value. Okay, and I would have the same for the ones for 2 all the way to P, V, or N here. Okay, so I have all of these. This will be another column vector, and I'm going to add this vector, okay, which represents all of this. Okay, and add this one over here to this one over here, and get a corresponding entry for all of the end states that I have here. Okay, like I said, it is a linear equation, and we can solve this directly through linear algebra. It's pretty simple. We first are going to collect all the v's. So I have a v over here, and I have a v over here. Let's gather them together. Right, so I'm just going to take it to the other side. To make it come out nicely, I'm going to have an identity matrix here, so that I will get v on the outside when I times it through. Okay, in order to solve for v here, then I have to take this and pull it over to the other side. I can do that through a matrix inversion. So I end up with identity matrix minus the discount scalar times the probability matrix. All of that taken through a matrix inverse times our column vector of rewards, and that's going to give us our column vector of value, state values for being in a particular state. Now, of course, this is going to be bottlenecked by this particular operation here, our matrix inversion, which is going to take cubic complexity. And that means, like many things in the case where we have to do inversion or anything cubic, it's really only going to be possible for small Markov reward processes. So when we have a large reward process, it's often the case in practice, we can't use this directly because the inversion is too difficult, takes too much time. So we're going to have to find some approximate methods, either by the stochastic optimization or dynamic programming, which is very common as well.